Hello everyone, welcome to lecture 2 of the online course on modern display technologies, flat panel display. Today's lecture will be on fundamentals of displays. So in this lecture, we'll briefly cover the global display market overview, and then we'll go into the physics behind displays. We'll talk about the fundamentals of light, coherence of light, and irradiance of light. So we've seen briefly that in the last lecture that the global display market, there's a forecast that this market will grow at a rate of 5.1% and will be a $173 billion market by 2029. And the technologies that will be dominating will be LCD and LEDs, the mini and the micro LEDs, and the other ones, OLED and quantum dot display, e-paper display, they will also see a lot more improvements. Okay, so the displays have now become essential devices in our day-to-day life because we constantly interact with some sort of display. Right now, while recording this lecture, while you are studying this content, you are also looking at some display. Okay, so try to find out what kind of display is it, in which category it falls. Okay, and that is how you will be able to link or correlate the contents that we are studying. So let us go and focus on each of these technologies, and let's see what is going to happen in each of these technologies over the next 5 years or 3 years timeline. So LCD market, liquid crystal display. Okay, so this market was valued at 148 billion in 2021, and it is going to become a $1422 billion market by 2029. So you can see the LCD, liquid crystal display market, is growing at a rate of 32.6%, and this is how the growth rate looks like. So this is basically data from the market analysis. So you can also see this by different regions like North America, Europe, Asia Pacific, South America, and Middle East and Africa. So you can see basically every region will have a lot of growth in terms of LCD. Now why LCDs are important? Because they are cheap. Okay, and there are some other factors also involved. LCDs will that's why become integral part of entertainment, retail, healthcare, education, transport, corporate sector, and they will be serving as the backbone of digital communication networks. So what are the growth drivers? So you see that there is an increasing demand of larger format. So people want to go for a bigger television or bigger display. So 50 plus inch, that is the kind of requirement every household now come up with to watch a cricket match or to watch any kind of movies. They want a very large screen. Okay, then people are going for higher pixel density, 4K, 8K televisions. You are also seeing that the automotive market, the new cars, they're coming with really big displays for infotainment or the digital clusters. Okay, odometer, everything is now becoming digital, and the laptop and even medical equipment displays are also now becoming high resolution. So what you see here from the region-wide trend is that the North America basically leads due to the strong retail demand and the supplier presence. However, Asia Pacific, which is this region, is poised for a major growth due to awareness of LCD benefit is going to rise. Then we come to the next competitive technology, which is the mini LED market. Okay, so you see what was mini LED market in 2021? It was very small, 162 million US dollar only. Okay, and that is supposed to become a 27.6 billion US dollar market by 2029. So a growth rate of 90%. So this kind of statistics basically tell you where the world is moving towards and which is the right technology where you should study and focus more. So why mini LED market is becoming very attractive? Because of the applications in consumer electronics, automotive, advertising, aerospace, defense, because they offer brighter and more efficient displays. Now what is the driver for this growth? The demand for the smart devices, IoT, next gen networks, and valued for durability and light efficiency. So this is the game changer. Okay, if your display is durable and it is energy efficient, so this is where it will be the winner of the market. So here also you can see North America basically leads with strong electronics demand. Okay, however, Asia Pacific is also rising with the semiconductor advances. Next, the more advanced version of this LED market is basically your micro LED, and it was valued at around 801 million in 2024. Okay, so it is only recently that you are started getting the data. Okay, and it is projected to surge up to 163 billion by 2034 with a growth rate of around 71%. Okay, so this is mainly the US based data shows that the market size in US was around 106 million in 2024. Okay, so what is the application of this micro LED? So they are mainly getting adopted in wearable devices, AR VR devices, augmented reality and virtual reality devices, automotive display, the premium TVs and digital signage. So this is where this micro LED is going to make an impact. So what are the growth drivers for this technology? There is always the demand for ultra bright energy efficient displays, which is rising with the popularity of smartwatches and fitness trackers. So they come with micro LED. Okay, and also you will see that there is expansion of the automotive digital cockpits, and a lot of cars these days started having the head up display. That means the display is basically your odometer details are basically projected near your windshield, so you don't need to look away from the road to see the other parameters. So these are called head up displays. So the region wise trend shows that Asia Pacific leads with nearly half the market share, while North America is the fastest growing region, supported by the semiconductor innovation in this particular product. Now if you look into the Asia Pacific market, so this region is projected to grow at the highest CAGR during the forecast period of 2024 to 2029. Okay, so Asia Pacific is currently a major hub for the production and consumption of display panels, which are driven by rapid technological advances and adoption of the display device market. So you can also see by end use application. Okay, these are the two colors showing 2029 and 2024 data. So LCD is going to be still the leader. Okay, but OLED is also catching up, but as I told you, OLED will have its own limitations. So people are also investing towards micro LED, direct view LED and other technology. If you see country-wise, you can see China, South Korea, Taiwan, Japan, they are basically leading. So we need to catch up in terms of technology, okay, for competing with these giants in Asia Pacific. So this region is an attractive market for the manufacturers of smartphone, tablets, laptops, TVs. Okay, so this actually plays a very important role in the consumer electronics industry. So the leading consumer electronics companies in this region, you already know, these are the Samsung Electronics, LG Electronics, Sony, Sharp and Panasonic, and they are all into prominent display manufacturing. So there are Samsung Display, LG Display, IO, Japan Display, Sharp. They are extensively manufacturing displays in their facilities across Asia Pacific countries. So altogether we understood that Asia Pacific region is projected to grow at the highest CAGR during this particular time. Okay. And with the adoption of digital teaching methods and the shift towards online and hybrid learning models, okay, people are also using this kind of displays more and more often. Something like, you require very high quality displays for video conferencing, interactive presentations and remote learning. So this growing demand for displays in education is expected to continue fueling this market growth, particularly in the Asia Pacific region. The increasing demand for consumer electronics, something like smartphone, tablet, laptop, TVs, they are also driving this advancement in technology. And we understood that the major manufacturers like Samsung, LG, Sony, they are all investing in R&D to develop cutting edge display technologies such as OLED, quantum dot, micro LED, which can enhance the consumer experience even more. But you have to keep in mind two factors, one is durability and the other one is power consumption. So what are the challenges? So all is not good here. So when you think of the display technology market, there are always very high cost associated with this new display technology based products. Okay. So the best thing that has happened to LCD is the declining of their prices of the LCD panels. They have significantly influenced the display market, okay, making LED LCD more affordable as compared to the newer technologies, that is like quantum dot LCDs or quantum dot OLEDs. Okay. So what is this LED LCD panels? They are basically using LCD to generate the different images, but for the backlighting they are basically using LEDs. Okay. So that is the most cost effective one. So the development of new technology always incur high cost due to the research and development and manufacturing, okay, and the low initial production capability. These things basically give you a premium pricing. Okay. So that is where sometimes the newer technology find it difficult to penetrate the market and the cheaper technology will continue dominating. So in that way LCD still has a long way to go, although there are different high tech technologies are competing or coming out every day. Okay. So high costs of new technologies basically limit their market product penetration, but production cost reduction and economies of scale over time can actually enhance this affordability and that will influence the adoption. So slowly people will see that when those high tech technologies, because they are good, when they will become cheaper, people will start adopting them as well. So now let us briefly look into the physics behind displays. So the first thing that should come to your mind when you think about display is that display is giving out light, right? So in order to understand the physical properties and if you want to design or fabricate any display technology, it is essential that you have a good understanding of the basic physics that involved in light sources and the different materials people use for light generation. So here the key principles basically involve the wave properties of light, energy transfer mechanism and polarization, which enables the control and manipulation of light. Because the polarization is one of the important concepts that you will see is utilized by LCD. For that, theoretical foundation such as Maxwell equation can provide a mathematical basis from which simpler concepts like rays, waves or polarization will emerge that can address most display related challenges. The modern concept of light has shown that it has got both wave and particle duality. Okay, so we talk in terms of photons and their properties. Okay, and this is the heart of the duality theory. And the simple way to understand the properties of light is to apply the correct theoretical mechanism to the problem that you are going to solve. So in the case of displays, most problems can be solved using either photons or through ray or geometrical optics, or by the wave propagation or wave optics. Okay. So, that will basically give you a complete understanding of what kind of physics is basically involved in displays. Now, a good mechanism for visualizing the propagation of light is in the form of rays or wavefront that you can see here. So, this is how we have seen in our school days, that this is a ray approximation for light, or you can also think of wavefronts. Okay. So, this is the propagation of direction. So, this is an basically idealized presentation, and it does not take into account what happens to small features or edges if that occur in the optical path. However, it is a very powerful tool for solving generic optical problems. A ray can be drawn as if extending from a wavefront, and a wavefront can be generated from a group of rays using Huygens principle of wavelet propagation. So, in most display applications, geometric ray theory will be used, but the wavefront could equally be applied to solve the problems. The wave properties of light can be used to generate waveforms which propagate like ripples, okay, on the surface of a pond. So, light propagation can be expressed both in space and time. However, the two dimensions are separable and you can solve them independently. So, typically a propagating optical wave can be expressed as psi equals a cos kz minus omega t, where a is basically the amplitude of the wave propagating in space z and time t. Okay. So, lambda is basically the wavelength of the light, where k is basically the wave number, which is 2 pi by lambda. So, that is how they are related, and omega is basically the angular frequency of the wave. So, this famous scientist on the right is James Clerk Maxwell. So, he basically forced the connection between light and electromagnetism, which was discovered by Michael Faraday. So, James Clerk Maxwell, he basically advanced the theory that light is basically an electromagnetic wave phenomena, and he formulated a set of fundamental equations which are of vital importance, and that is why they basically bear his name, and this is applied to all electromagnetic waves. So, using the terminology of the vector calculus, you can write these 4 equations. Okay. So, the first one is Gauss law. Okay. So, it tells you that the electric flux out of any closed surface is proportional to the charge enclosed within that surface. Okay. The second one is also called Gauss law of magnetism. So, it tells you that the net magnetic flux out of any closed surface is 0, which also tells you that there is no magnetic monopole, possible, right. Then you have the Faraday's law, which tells you that curl of E equals minus dou B dot T. Okay. That means changing magnetic field can produce a circulating electric field. So, I believe all of you know these basic terminologies. So, D is basically the electric flux density, B is the magnetic flux density, E is the electric field vector, and H is the magnetic field vector. Capital J is the current density, and you see rho here is charge density. Okay. And the final equation is Ampere's law. Okay. It states that the generation of magnetic field can be done in 2 methods. So, either you can have electric current, okay, or you can have time varying electric field, right. So, this equations together are known as Maxwell's equations, and these equations show that each field vector basically obeys a wave equation, that a varying electric field is accompanied by a varying orthogonal magnetic field and vice versa, and that the two form an electromagnetic field that can basically propagate in the form of a transverse wave. So, Maxwell's insight basically paved the way for Heinrich Hertz to discover and identify radio waves and to show that they behaved in a very similar manner to light. Okay? And the discovery of further ranges of this electromagnetic radiation led people to construct this kind of electromagnetic spectrum, which basically runs from this lowest usable radio waves to the highest frequency possible, that is the gamma radiation, right. Here you can also see that the visible part of this enormous spectrum covers barely an octave. Okay. So, it has a wavelength range of approximately only 380 to 780 nanometer. So, this is what we see. So, our displays are basically only working in that tiny range. Okay. And this is somewhere in falling in between the solar spectrum. Okay. So, solar spectrum has got a bit of UV, then it has got this visible spectrum, and then rest is IR. Okay. So, this figure basically tells you the wavelength range which we are bothered about when we are talking about displays. Now, there are certain properties of light that also plays an important role. One is coherence. So, if we assume that light has a basic wave property as we already described, then we are assuming that light is also fully fully coherent. Now, unfortunately, such light sources are very rare where the light is fully coherent. Okay, means now the photons are all in the same phase relation. Okay, even the highest quality laser light source will also have some degree of unpredictability. So, the measure of this unpredictability is basically referred to as its coherence property, and it is expressed in terms of the source coherence length. So, the figure basically shows this is the source and this is how it is predictable till here. So, this is the coherence length. So, coherence length is basically defined as the distance the light propagates before the ability to predict where you are on the wave is basically lost. So, you can predict the wave till here. So, this is the coherence length. Now, for example, why is it not possible to see the diffraction pattern from a compact disc of CD when viewed with a thermally random light source such as tungsten filament light bulb? The answer lies in the relative size of the feature on the CD with respect to the coherence length of the light source. Okay. So, as long as the feature size is of the order of or less than the coherence length, the diffraction effects will be seen. So, we understood that the thermal sources such as tungsten filament light bulbs, they tend to be very random. So, they have very short few micron only as coherence length. In contrast, when you look into sources which are based on stimulated emission, which are trapped within a defined optical cavity, which you see in a laser, they typically have very long coherence length in the order of meters. Other light sources such as arc lamp or LEDs, they are basically LEDs, light emitting diodes. They are often classified as partially coherent, as they basically sit somewhere in between these two extremes. So, your tungsten filament light lamps are completely incoherent, or you can say very short coherent length. Lasers, they have very long coherence length. So, LEDs are also incoherent, but they are somewhere in the middle. So, the most important reason for defining coherence property of the light source is that it dictates why propagation theory and principles, it actually tells which propagation theory and principles can be used to understand its property within a given application. So, if you take coherent sources such as lasers, which have high degree of predictability. Okay. So, they are subject to rules of diffraction, where constructive and destructive interference can occur between the waves as shown below. So, when they are all in phase, you can have constructive interference. When they are completely out of phase, they cancel out each other and you get destructive interference. Now, on the other hand, if you see incoherent light sources, they can be modeled using very simple principles based on average energy and direction of propagation, as you can see here. Okay. So, the majority of the optical design that is done in displays is based on either harnessing or suppressing the effects that can be due to the coherence properties of the light source. So, in this case you can see this is the RMS effective time average. So, this is basically the incoherent interference of the waves. Now, as majority of the light sources are relatively incoherent, simple geometric rules as used by ray tracing can apply. More recent developments into bright arc sources and LEDs along with laser projection, both holographic and direct, have meant that it is increasingly important to understand the coherent diffraction based light properties for a given display system. Next important feature is the irradiance of light. So, this important property tells you how it transports energy. Hence, it is logical to represent this property as energy density or radiant energy per unit volume. So, in terms of electric field or magnetic flux density, okay, electric or magnetic flux density, you can write U equals epsilon naught E square, that will be equal to 1 over mu naught B square. What is epsilon? That is basically the vacuum permittivity, and mu naught is basically vacuum permeability. Now, to represent the flow of electromagnetic energy, let us S represent the transport of energy per unit time, that is the power across a unit area. So, if you assume that the energy is flowing in the same direction as that of the propagation, we can express this S as a vector, and this is the Poynting vector, as you all know, that can be calculated as half E cross H. So, this is the electric field vector and this is the magnetic field vector. So, the magnitude of S is the power per unit area crossing a surface whose normal is parallel to S and is often offered as the Poynting vector, as I mentioned. So, E here is the electric field, H is the magnetic field, and all of you know the relationship between B and H. B equals mu H, that is the magnetic flux density is basically the permeability of the medium times the magnetic field. Okay. So, these are always electric field and H, they are always orthogonal to one another. So, at optical frequencies, this is very fast indeed. Okay. So, it is often logical to talk about the time averages of such quantities. Okay. So, how do you calculate time average? So, the time average value of the magnitude of the Poynting vector can be symbolized as this, and this you can tell as the irradiance I. So, I is calculated as this time averaged value of the Poynting vector, which is basically epsilon naught C and then the time average value of the E square. You can also write it as C by mu naught and B square. So, to summarize what we have seen, a display engineer does not require a very in-depth knowledge of the Maxwell's equation, but he or she needs to understand the fundamental physical properties of light that controls the that basically leads to control, propagation and modulation. Optical coherence, which is also derived from these properties, basically determines the applicable rules for understanding light interactions with display technologies and their environment. Okay. So, the key to this will be an understanding the basic properties of light and how this leads to an energy transfer. The wave properties of light influence the display performance, including the wavelength and the color control, optical efficiency and the dispersive effect. These aspects can be effectively analyzed using simple properties and models to evaluate the display functionality. So, by using simple analogies, a very powerful analysis can be made as long as the correct assumptions about the fundamental properties of light sources and its propagations are well defined. So, with that we conclude today's lecture. If you have got any query, you can drop an email to this email address deb.sikdar@iitg.ac.in mentioning the course name on the subject line. Thank you.